We had lecture 21, which built upon several properties of vector spaces that we've seen before. First, what is an eigenvalue? And a property that only complex operators have is that they always have n eigenvalues if we count multiplicity, where n is the dimension of space, of course. And this comes from the fundamental theorem of algebra. And it's convenient then to complexify real operators so that they also have n eigenvalues. And this way we defined the characteristic polynomial of an operator as simply the product of z minus lambda over all eigenvalues lambda, the eigenvalues of the complexification. So the characteristic polynomial of an operator always has degree n. Then another thing that we use and that we saw a long time ago, it also comes from the fundamental theorem of algebra, is that it's always possible to find the basis for a complex vector space such that your operator on that space, represented as a matrix with respect to that basis, is upper triangular. And then in this lecture, lecture 21, we defined the trace of an operator as the sum of all its n eigenvalues. So we take the complexification of the operator, look at those n eigenvalues with multiplicity, sum them, and we call that the trace. Then, so for that, we of course use complexification, and then we remember what the characteristic polynomial is, and we expand that product and see that the trace, it appears as a coefficient of the characteristic polynomial if we expand and write the characteristic polynomial as just a sum of monomials explicitly. Then we saw the definition of what's the trace of a matrix. That's something very simple and straightforward to compute. We have a matrix, we add the elements of the diagonal, and that is the trace. And that these two objects are very well connected, and that's why they have the same name. They are very well connected, and the trace of an operator equals the trace of the matrix of that operator with respect to any basis. All bases that you choose to represent your operator, it won't matter, the trace will be the same. And that's an amazing property that matrices have, is that their trace does not change when we apply a matrix on the left and on the right that correspond to a change of basis. So if we multiply a matrix by an invertible matrix on the left and its inverse on the right, this will not change the trace, and this follows from the fact that trace of the product of two matrices A times B is the same as the trace of the product of two matrices B times A. Now there is one point here that I want to stress, which is that when we compute the trace, we have to sum the eigenvalues of the complexification of T, not just T itself. And another point I'd like to stress is that it is true that at this point the applications or practical uses of the trace, or even theoretical uses of this concept, are less clear at this point. Let me just mention that the trace is related to taking average in some sense. Well, in which sense? AII we can think as the result of applying a matrix A to some vector EI and then taking the inner product with that vector again. And this inner product, we can think of this as some average, especially if later on, instead of having the index I in 1 n, we now have a continuum of indices, and the dimension, instead of being a finite dimensional is a continuum dimension. Another very interesting and useful identity involving the trace is that if we take the exponential of a matrix, this, and compute the determinant, this will be exactly the exponential of the trace of A. So this is exponential here, is just the exponential of a number. We have a matrix, we compute the trace, we get a number, we take the exponential of that number. And here e to the A is a notation that means identity plus A squared divided by 2 plus A to the k divided by k factorial plus, we compute this infinite sum of matrices, we call it e to the A, we compute the determinant, we get e to the trace of A, and this concept is a very useful concept in many branches of mathematics. And this was the summary of today's lecture. I hope it is useful and we can discuss in the forums if there is any further questions.